The purpose of this brief video is to prove two theorems, Theorem 10.1 from your book, as well as Theorem 10.2. These are both theorems that relate to circles. Theorem 10.1 states that if a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So that if L is a line which is tangent to a circle with a center of Q, and the point of tangency is at P, then the line L is perpendicular to QP. And this is a picture of that theorem. So here we have a circle with a center of Q. We have a line, L, which is tangent to the circle with center Q, and it touches the circle Q at point P, which is known as the point of tangency. The theorem states that the line segment QP is therefore going to be perpendicular to line L. And now we're going to try to show why that is the case. So we have this diagram here, and this diagram shows circle Q, circle with center Q, and a radius QP, and a line that is tangent to the circle at point P. And we also see that we have a label of another point that is on the line that is not at the point of tangency. We call this point R. In general, R could be any other point on the line. So why then is QP perpendicular to line L? Well, there are certain properties of the points along this line that we can see immediately from the diagram. Since this line is a tangent to the circle, it means that every point other than P is going to be outside of the circle. P is the only point which lies on the circle. That implies that any line drawn from the center Q to another point on the line other than P, such as line segment QR, is going to be of a greater length than line segment QP. That is because line segment QR extends from the center of the circle to the circle itself, right over here, but then beyond the circle for a certain distance in order to go outside the circle. So that means that line segment QR is greater than the radius of the circle, and since line segment QP is the radius, is of length radius, then line segment QR is always going to be greater than line segment QP. Well, that's another way of saying that line segment QP is the shortest distance from Q to the line. So if QP is the shortest distance from Q to the line that's tangent to the circle, we already know from other theorems in geometry that the shortest distance from a point to a line is the perpendicular from the point to the line. So we have just proven that QP therefore must be perpendicular to this line, and we could demonstrate that by drawing in a little perpendicular sign, and it turns out that that is exactly what we need to prove in order to prove the theorem. So we are done with Theorem 10.1. Well, let's take a look at Theorem 10.2 and see what that says. Okay, so going to Theorem 10.2, we see that Theorem 10.2 says, in a plane, if a line is perpendicular to a radius of a circle at its endpoint on the circle, then the line is tangent to the circle. Well, that's sort of the converse of what we just proved in Theorem 10.1. So let's look at the diagram here. So in this case, we're given that QP is perpendicular to the line that meets the circle, that goes through point P from the radius QP. And what we need to prove is that this line is a tangent. Okay, so it's actually fairly easy to prove with what we know already. So we have the same diagram now. We have QP is a radius, P lies on the line and it's perpendicular. to QP. And now we have to prove that this line is actually a tangent. Well, we know that QP is perpendicular. That's another way of saying that the distance QP is the most direct distance from the point Q to this line L. Well, that would mean, therefore, that any other point along the line, such as R, would have to be at a greater distance from Q than P is. Well, if it's at a greater distance from Q than P, it must be greater, the distance must be greater than the radius. Therefore, it must lie outside the circle. We've just proven that every other point other than P on this line L must lie outside the circle. But that is nothing other than the definition of a tangent line. So we have just proven both theorems 10.1 as well as theorem 10.2.